Hi, my name is Scott Simpson, and today we'll be talking about mass spectrometry. So in mass spectrometry, you're using this instrument to basically determine the composition of a substance or the molecular formula of a substance. Based upon fragmentations, you can identify the compound. So what happens is a molecule goes into the instrument, it gets fragmented, and it spits out these fragments, which are detected. And from these detected fragments, we can piece together or get kind of like a chemical fingerprint for a compound. So what you use it for, it's used to determine composition of a substance. And one type, the type that you'll be using in lab this week, is known as electron ionization, or it's also known as EI. And it's used to produce ions. Okay, so let's talk about the inner workings of the mass spectrometer. To do that, we're going to draw a schematic and explain what's happening on the inside of the mass spec. Now, mass spectrometers, they all work sort of on this principle. They don't work all exactly this way. We're going to look at one that's called a time of flight mass spectrometer. That's probably the easiest one to explain. So we have a sample. So here's our sample. And we need to make ions. So the way that this is done is you have an ion source. In this case, it tends to be some sort of filament. So this is our ion source. What happens is you're generating electrons. Now, the electrons actually won't propagate through space this way. What you have to do is you have to put a positively charged plate. So the electrons, when you produce them, hit the sample, and hopefully they make it to this positively charged plate, causes them to go in that direction. Then what happens is you get fragments. Some are charged, some are not. The ones that aren't charged, they get filtered out, but the ones that are charged, what happens is they go through a set of magnets. And they get deflected based upon their mass to charge ratio. They get detected, and that's the output that we see, and that's what you'll be using. So let's talk about this process, this ionization process. Ionization and fragmentation. So like we said, in order to be detected or deflected, to make it to the detector, the species or the fragment has to be ionized. It has to have a charge on it. So one sample gets ionized, it can be detected. So as an example, let's consider methanol. So this is what the structure of methanol looks like. It's 2 carbons, a handful of hydrogens, and a single oxygen. Go it that way. And if we hit it with a fast electron, what will happen is we'll knock off one of the electrons in this system and we'll create a charged species. COH, H. So positive charge, And then what happens is we'll get a slow moving electron and we'll get a fast moving one. Now, if we look at what we see in the mass spectrometer, we wouldn't see this species, but we would see this one. And it would have a mass to charge, or an N to Z ratio, of 46. So where do we get this number from? Well, we look at each individual isotope for each individual atom and we sum them up. Generally, we look at the most common isotope. So in this case, for hydrogen, it would be H1 rather than, let's say, deuterium, where you have two particles, one proton and one one proton and one neutron in the nucleus, or tritium, where you would have one proton and two neutrons in the nucleus. So this mass to charge ratio is very important. If the species is not charged, it will not be detected. So note, uncharged species do not appear in the mass spectrum. Okay, but sometimes a really fast electron will hit a system, and what it will do is it won't knock off just a single electron, and like in this case, it'll actually break a bond. So let's see an example of that. So sometimes a really fast or an additional electron will fragment the molecule. So in this case, we start with our molecule, or ethanol. And this guy has a positive charge. What will happen, we could actually break this guy apart. What we're going to do is we're going to pull off a hydrogen and we're going to pull off this OH group. So we get two species. Okay, now if we consider what we'll see in the mass spectrum, we have a mass to charge ratio. This pen will work. M to Z for this guy, we've already said what that was, that's 46. But what about these two? Which will show up in the mass spectrum and which will not? Again, we have to consider if there's charge on these species. This water molecule is not charged, therefore it will not appear in the mass spectrum. However, this portion, this positively charged portion, will. And we can predict what its mass to charge ratio will be, because we could look at each individual nuclei, we could sum them up and we could get an answer, or we could consider the fragment that broke off. We know that each of these protons is worth 1 AMU, and then we have the oxygen, which is worth 16. So if we subtract off 18 from our original value, we'll get the mass to charge ratio. So there's a couple different ways to do this. So in this case, if you do that, subtract 18 from this, or you add up the masses of all of these, we get a mass to charge ratio of 28. So this species on this side would show up, whereas this guy, this water molecule, would not. So that brings us to another question. Why do we see exactly 46 AMU in the mass spectrum rather than 46.069 AMU? So this number comes from the average atomic mass on the periodic table if you add those up all for ethanol. So why don't we see this in the mass spec, but we see this guy? Well, remember, when we're looking at the periodic table, this is a large ensemble of those elements or those atoms. So it's a weighted average that we're considering. When we use the mass spec, we're actually looking at individual molecules. So the mass spec is looking at individual molecules. And we said the value, looking at individual molecules, and this value of 46.069 AMU is a weighted average. And what it does is it considers the percentage of all the different isotopes that make up this compound and the relative abundance of them. And it's a summation of that average value rather than looking at an individual molecule. So keep that in mind when you conduct this next lab. That's a very important topic. If you have any questions, please leave comments below or feel free to email me. Thank you.